me share the screen. Yeah, so up to this we have done. Screen is visible, right? Screen is visible. Any one of you can respond.
Yes, visible, sir.
Visible, right? Visible. Okay, fine. Okay, so next write down. We have next alkyl lithium. Alkyl lithium. So basically, this alkyl lithium is represented like this. RLi. Okay. Now very simple, lithium is a metal, so it will be what? Delta positive charge, or you can say positive charge, positively charged, and alkyl group will be here negatively charged. Okay. So write down number 1, metal halogen exchange. Okay. Metal halogen exchange. Metal halogen exchange. Okay. So suppose I have this. This is what? Bromobenzene, right? Bromobenzene. And suppose here I am giving this reagent, butyl lithium. Okay, butyl lithium. So that means what? Lithium is positively charged, butyl is negatively charged, right? And when you have bromine, so what will happen here? The metal will exchange with the halogen. See, I have already written metal halogen exchange. Here don't think butyl minus will attack here, bromine will leave. It will not happen like that. Okay, butyl minus will attack here, bromine will leave. It will not like that, because addition elimination or addition elimination mechanism here it will not follow. Okay, so what it will happen here, this butyl minus will attack the bromine. Okay, and this bond will break like this. Okay, now butyl minus means what? Butyl minus means this, right? This carbon ion, this is actually not stable. Okay, this carbon ion is not at all stable. Okay, so butyl minus is attacking on the bromine, and what it will form? It will form butyl bromide, which is a stable product. And what you are getting now? So that, see, the electrons are coming to this benzene ring, so that means negative charge is forming there. Okay, negative charge is forming there, and you have lithium plus, so you can attach the lithium, you can show like this. Okay, otherwise you can simply write down what we are getting. We are getting pH minus lithium plus. Clear? Clear what is happening? Metal halogen exchange. So here this alkyl part is attacking on the bromine. Now when it will attack? If you have halogen, then only it will attack. Okay, so I am writing simply here. Suppose you have this, any halogen can be present there, not fluorine. Fluorine is not a very good living group. So chlorine, bromine, iodine. Okay, any type of halogen you can have there. If you are treating this compound with butyl lithium, okay, and when you are handling this kind of alkyl lithium, you have to maintain a very low temperature. Okay, usually minus 78 degrees centigrade, because it is very reactive. Okay, and what you will get? You will get this. Okay, clear? Clear?
Yes, sir.
Clear, right? Done. Okay, write down number 2. Number 2, write down acid base reaction. acid base reaction. So suppose you have phenol here, you have phenol, and here I am giving butyl lithium. What will happen? So again lithium is positively charged, butyl is negatively charged. Here oxygen is negative, hydrogen is positive. So what will happen? Butyl minus will take up the proton, and what you will get? You will get thing like this, OLi. Oxygen is negatively charged, lithium is positively charged. Clear? And butyl minus is takes up the proton, okay, because it's an acidic proton. Okay, now suppose I am treating this compound with methyl iodide, CH3I. Okay, methyl iodide. So what will happen? This O minus is attacking on the carbon center, and iodine will leave from here. Okay, so what I am getting? SN2 reaction, right? This is the nucleophile you have. It is attacking from the back side of the carbon atom, and this carbon iodine bond is breaking, SN2 reaction. So from phenol you are getting anisole. Clear? Acid base reaction is clear to all. Here I cannot see like Google Meet. Okay,
Clear.
clear, right? All of you clear na? Nayana clear?
Yes, sir.
Clear, right? Fine. Okay, write down number 3. 1 2 direct addition. 1 2 direct addition. So what is 1 2 direct addition? It will be like this. Okay, so suppose here I am taking this CH3Li. Okay, methyl what? Lithium, methyl lithium. So I think I have mentioned what is your hard center, what is soft center, that you know, right? If you have hard reagent, that will do what? That will do 1 2 attack. If you have soft reagent, that will do 1 4 attack. So what is 1 2 1 4? This is 1 2 3 4. Now which one is basically hard reagent? Suppose you have Grignard reagent. Okay, RMGX. Suppose you have alkyl lithium. These are basically your hard reagent. What is soft reagent? Soft reagent means like this. Suppose you have Gilman reagent, so RMGX plus UI. Okay, or Gilman reagent R2CuLi. These are basically your soft reagent, copper containing. Okay, so here if you have this lithium containing or magnesium containing, these are actually known as hard reagent. Okay, because lithium is positively charged and this is negatively charged, they are very reactive, that's why. Okay, so what will happen now? CH3 minus will directly attack on the carbonyl carbon. 1 2 attack it will do. Okay, so what I will get? CH3 and what? Initially you will get O minus, and after acidification you will get OH. Clear? Hard concept, soft concept we have done, right? Hard reagent will do 1 2 attack, soft reagent will do 1 4 attack. What are the hard reagents? Suppose you have Grignard reagent or this kind of alkyl lithium species, these are hard reagent. If you have Gilman reagent or with Grignard reagent, you are adding copper iodide, okay, cuprous iodide, so that is basically become soft. Okay, so if you have soft, that time it will attack in this carbon center 1 4 attack, and if you have hard reagent, that time it will attack on the 1 2 center. Clear? Done?
Yeah, sir.
Done, right?
Done, sir.
Done. Down next number 4, that is actually known as your transmetallation. In organometallic chemistry we will do it. Okay, transmetallation separately. So transmetallism means what? Transmetallism means retention in stereochemistry. Retention means what? Retention means there is no change in the stereochemistry of the molecule. Okay, there is no change in the stereochemistry. Okay, suppose I have a molecule like this. So organometallic chemistry, like this is carbon tin bond. Okay, SnBO3 group is attaching here carbon tin bond, and here you have what? Butyl lithium. So again see, lithium is positive, butyl is minus, negative, right? And here the tin center is positive, right? Tin center is because carbon tin bond. If you have carbon tin bond, so tin will be positively charged, carbon will be what? Carbon will be negatively charged, and then this tin will be positively charged. So butyl minus will attack on the tin center. When it attacks on the tin center, this bond will break. Okay, and if this bond breaks, what I am getting? Here I am getting a negative charge, and see what left? Lithium plus already left. You can show like this, or you can form a bond with lithium. Clear? Clear? Now suppose you are treating this compound with any electrophile. Electrophile means what? E plus. Okay, electrophile is what? Electrophile is E plus. So this electrophile will approach from the same side. Okay, where the tin group was present, the electrophile will approach from the same side. So that's why we are calling it retention of stereochemistry, retention in stereochemistry. Clear? This thing is clear. Simple thing. See, we are doing nothing. Butyl is minus, lithium is plus. Here tin is plus, carbon center is minus. So this butyl minus is attacking on the tin plus. So what will happen? This bond will break. Once the bond breaks, you are generating here negative charge, and what you have? Lithium plus is already present there. Now this negative charge can attack any electrophile depending whatever the reagent you are using. So it will attack the electrophile and you are getting corresponding product. But one thing you have to note, that whenever you are doing this kind of transmetallism reaction, so that time the stereochemistry will not change. Okay, you will understand it better when we will do organometallic chemistry. Okay, clear? Kaveri,
Yes, sir.
Nayana, okay. Isa, Sampriti, Chandana, clear?
Can we say Li is above the plane like that?
Here,
Above
the plane means?
Like if there's a bond there, I mean not technically, it will be.
No, here no need to show any stereochemistry because these will act as ions, okay? Because this carbon lithium bond actually does not exist. It's not a covalent bond, it's an ionic bond. Okay, so it will exist like this because whenever taking these compounds in solutions, they will always act like this. Okay?
Yes.
Okay, fine. Now write down number 5. This is very important. Ortholithiation. Ortholithiation. Okay, so first of all write down some points. Write down, it will follow your chelation mechanism. Chelation mechanism. Okay, so suppose I have a system like this. This is a benzene ring. Here you have electron withdrawing group. Okay, electron withdrawing group, and these are basically your ortho hydrogens, right? Ortho positions you have hydrogen. So write down that what? Presence of electron withdrawing group. Presence of electron withdrawing group at ortho position what? Increases acidity. Okay, so this is the one and only condition for ortholithiation. The name itself says ortho, so that means if you have some electron withdrawing group, the protons or the hydrogens which is present on the ortho position, that becomes what? Acidic. Okay, that becomes acidic, and once it becomes acidic, the alkyl lithium species will abstract this proton very easily. Okay, clear or not?
Yes.
Clear? Okay, let me give one example. Suppose you have this. This is what? This is the anisole compound, right? Now here I am giving butyl lithium. Okay, butyl lithium. So what will happen? Tell me, any one of you. See, this is ortho, this is also ortho, so both are same. Any proton it can take up. If you are using one equivalent, any proton it can take up. So lithium is positively charged, butyl is what? Negatively charged. So what will happen? Butyl minus will abstract the proton, and what will happen? What you will get?
4-membered ring.
4-membered, that is the transition state, right? Butyl minus is taking the proton, so this bond breaks. So what you will get? You will get this, right? Is it clear or not? Not clear?
Yes, sir.
Clear, right? Okay. Fine.
Sir,
Yeah.
if all 5 possibilities are present, for example, in one molecule we have bromine, we have OH, we have alpha, beta, everything we have.
Okay.
But we have only one equivalent of
Everything if you have, I think that kind of molecule they will not give. But yeah, if they give, keep in mind this acid-base reaction is the fastest reaction. Acid-base reaction is always the fastest reaction because it can happen in nanosecond only. Okay, that is one thing. And if you don't have that kind of acidic proton, if you have this kind of halogen, if you have halogen basically, that time metal halogen exchange will definitely take place. Okay, so if you have halogen, that time you have to consider this. Alkyl lithium is basically responsible for all these categories: metal halogen exchange, acid base reaction, 1,2 direct addition, transmetallation, okay, as well as ortholithiation. So they will not provide a system that make controversy like that. Okay, but keep in mind acid base reaction is the fastest reactions in our chemistry. Okay. Okay, so suppose you have this molecule and here I am giving butyl lithium. What will happen?
metal halogen exchange.
Metal halogen, fluorine cannot take part because fluorine is not that much. Carbon fluorine bond is very strong due to high electronegativity of fluorine. See, here I have not mentioned fluorine. Here I have mentioned for chlorine, bromine, iodine. Okay, carbon fluorine bond is very strong due to high electronegativity of fluorine. Okay, so metal halogen exchange is not possible here.
Ortholithiation.
Ortholithiation will take place. So which proton it will abstract, this or this?
Next to OMe.
Next to OMe. So see, Here don't abstract the proton from this fluorine. See, basically oxygen and fluorine. So if I see, fluorine is more electronegative, right? So basically this hydrogen is more acidic. If I compare the acidity of this HA and HB proton, so HA is more acidic. Okay, but why HA is not abstracted by this alkyl lithium species? Because it follows a chelation mechanism. Now how does it chelate? So basically, if I compare the donor ability of fluorine and oxygen, so which one has higher donor ability? Definitely oxygen, because it is less electronegative, right? So oxygen will donate the lone pairs to what? To lithium. Okay, because lithium plus is there, and see, here you have butyl. So now butyl will abstract the proton. So that is the chelation mechanism is actually happening. Clear? What is happening here? Here you have no competition, that's why any proton you can abstract. But when you have a competition, don't think that this is more electronegative, so the proton will be abstracted from here. You have to first of all check the chelation property, okay, which can chelate it better. Now why fluorine has also lone pairs, but why fluorine is not chelating this species? Because fluorine is more electronegative. Okay, it cannot donate the electrons so easily if I compare with oxygen. So oxygen can easily donate the electrons to lithium, and that's what actually chelation property. Clear? So what is happening? Butyl minus, this takes up the proton, okay, and then you will get this. So here I have OMe, okay, here I have fluorine, and here you will